last class we studied about various phase control converters, that is control rectification, how we can get variable DC voltage. Okay. Now, and then variable DC voltage with improved power factor, then finally we come to the front end AC to DC converter with the unity power factor, and how it can be controlled using sine triangle comparison, and also without resorting to high frequency PWM, how we can suppress the low order harmonics. Okay. So, now we know that we can get a variable voltage, and as I told explained before, in the case of AC to DC converter, 4 quadrant conversion is possible. That is, power can flow from AC side to the DC as well as DC side to the AC side. Okay. So, 4 quadrant operation is possible there. Now, let us with this one, let us go to our speed control system for a motor. So, here we will take first separately excited DC motor. Separately excited, this is with respect to field winding, excited DC motor speed control. We are going to talk about the DC motor speed control. Okay, a separately excited DC motor, we can represent it like this, schematically like this. Okay. Here you will have the back EMF EB, then the motor armature resistance and inductance here. Okay. And this is the applied voltage V, then speed of rotation, here field winding. Field winding will be excited with the rated field current. So, we will use a separate rectifier, we will rectify the mains with the inducing diode rectifier according to the rated voltage and give it to the field. So, field will be excited. Now, let us say the motor is running with a speed omega. Now, we are applying DC voltage. So, the inductance will not come into picture. We can assume the current through this one is IA, I DC current. Okay. So, if you write the equation for the terminal voltage, it will be V is equal to I into R plus EB. EB is the back EMF. This is the relation between EB and V. So, this is the R. Okay, V is equal to IR plus EB, and we are going to have a speed control of the DC motor. For speed control, any speed control change, that means we want to accelerate the motor, decelerate the motor, we have to give a correct torque applied to the machine. So, what we want the torque, typical torque speed characteristics of the machine. Okay. So, let us start from this equation, V is equal to IR plus EB. We know EB is equal to the back EMF. So, you have the flux orthogonal to the winding, the construction itself is like that, and the windings because of the rotation, there is a relative motion between the windings and the field, and a back EMF is generated. So, E is the back EMF. R is the armature resistance. Okay. So, now what is EB? As I told, EB is proportional to omega. Okay. So, proportional to omega means we can write it this, EB is equal to some constant K, that depends on the machine, and the flux generated due to this field winding, flux and rated flux. We are given the rated flux K phi and the speed. Speed is a function of time. Okay, Eb is equal to k phi omega. Now, we will substitute this equation 2 into 1. Then see, now we are going to introduce the omega into this equation. Then later we have to introduce the torque. Then from this we have to get the relation between the torque and speed. Then we will find the torque speed characteristics of the machine for variable conditions. So, Eb is equal to k phi into omega. Now, when you substitute this one, this will be equal to V is equal to IR plus k phi into omega. Okay. This k phi is a constant for a machine. From this one, what is omega? Omega is equal to V minus IR, that is the armature drop, that depends on the resistance and the load current. Sometimes we can neglect it also. So, V minus IR divided by k phi. See, we are going to have the control of the machine through V. So, for a speed control omega here, this the only parameter we can control is the V here, that is applied voltage, armature voltage. Okay. Now, we want the torque speed characteristics. How we find out the torque speed characteristics? We know the power generated in the machine, that is P is equal to Eb into I, power generated in the machine, not V into I, because there is a loss here in the R. So, after that only we are getting a there is a loss, after the loss only the rest power only going to the machine. So, the machine the power generated in the machine is equal to Eb into I, V into I, that is equal to k phi omega into I. Okay. Now, we know that P is also equal to torque into omega, also proportional to torque into, oh sorry, it is also equal to torque into omega. Okay. P is also equal to k phi omega into I. So, from this equation, what is P by omega? P by omega is equal to torque, that is P by omega is equal to torque is equal to k phi into I. So, P power is equal to k phi omega into I and power is equal to T into omega. So, P by omega is equal to torque is equal to k phi into I. So, if you see here, for a machine this k phi is a constant, that means torque will be proportional to the our input armature current. So, to vary the torque we have to supply a variable Ia depending on the torque. To increase the torque we have to increase current, to decrease the torque decrease the current Ia. Okay. So, T, now this equation, this is the fourth equation. Let us substitute this equation to this omega. So, if you do it, omega is equal to V minus I is equal to, what is I? I is equal to T by k phi. So, T by k phi, okay. V is equal to, omega is equal to V minus IR into R divided by k phi. Okay. This we can again write it as omega is equal to V by k phi, this is a constant, minus T by k phi whole square into R. So, we got a relation between omega and the torque T. Okay. This is this one. Now, let us take, we found that torque is proportional to I, okay, and omega also depends on the I here. When we have the maximum speed is when t is equal to 0 or I is equal to 0. I is equal to 0 means there is no load. Okay. So, this is the omega 0. The maximum speed for a particular V is omega maximum. For a particular V is equal to V by K phi. Okay. Now, how will, from this one, how we will get the torque speed characteristic? Let us see. This is our torque and this is our omega. Now, from the previous equation, we will write the equation again here for our reference. Omega is equal to V by K phi minus I divided by K phi square into R, and omega maximum is equal to V by K phi. So, the maximum speed depends on, for a no load with the no I is equal to 0, it is proportional to V, okay, V by K phi. So, here also if you see, this also equal to the maximum back EMF. When I is 0, I is equal to 0, IR drop is equal to 0, V is equal to EB. So, that means this is also equal to, V is equal to K phi into omega. Okay. This is the back EMF. So, V will be equal to back EMF. Now, let us plot the torque speed characteristic for a particular V. So, we have fixed the V. We are not, once the fixed the V, and when EB is equal to V, we have the maximum speed here. Okay. Now, as I increases, due to the second time here, as I increases, what will happen? The speed will slowly decrease, speed will decrease this way from the maximum speed. This depends on the R, I into R. See, I depends on the load. So, R depends on the load. That means load means the torque demanded by the load. So, I torque is equal to K phi I. Okay. So, what is the torque demanded by the load? That depends on the I. Now, if you see here, can we have a speed control of the machine for a, let us say torque is fixed, load torque is fixed. This is the load torque what we want. Okay. T load. Okay. Now, so I is fixed. Can we have a speed control here? If you see this equation, V is fixed. So, the maximum speed is fixed. Now, how we can have a speed control? Suppose I increase the resistance R. R is the armature resistance. If I increase the R, this drop will become like this. So, for different R, we can have for the same load, by introduce more and more armature resistance, we can control the speed. This type of speed control we have done before, where we can see with the lever while we are increasing the armature resistance and decreasing armature resistance. Okay, that way we can increase the speed or decrease the speed by varying the armature resistance. So, let us say this is R1, this is R3, this is R4. So, if you see R1 less than R2 less than R3 less than R4. So, as R4 increases, resistance increases, the speed decreases. Okay. Now, but this type of speed control system, it is not very, it will not give very good dynamic performance, because it has to increase the resistance and decrease the resistance. It is done manually. Okay, it is a slow system. What exactly we want? We want in a system, especially in modern electric drive, it is frequently necessary to stop the drive or quickly accelerate or reverse it. So, the torque speed characteristic should be not only in this quadrant, it should be in all 4 quadrants. That means, we have talked about the 4 quadrant operation. If you write here, see, as I told, we want to accelerate, decelerate, speed reversal, all those are required. So, if it is omega, this is T. See, this quadrant, let us say forward motoring. Okay. Now, and with the same speed, suppose I want to reduce the speed. Reduce the speed means what I should do? For reducing the speed, see, motor is running, we have to take back the kinetic energy from the system and supply back to the source. That means there should be, we should apply say reverse torque with the same speed. So, here that is called braking. Torque will be negative, speed will be in the same direction. This can be also say forward braking. Then both omega and torque are negative. Omega, torque are negative. So, what will happen to power? We know P is equal to T into omega. So, when both the torque and omega are negative, that speed is also reversed, torque is also negative, if you say, then power is still the positive. That means it is still, it is called reverse motoring, same like our forward motoring. This is called reverse motoring. Okay. Now, in this case, torque is the other direction. So, it is called braking. So, we want all 4 quadrant operation. So, if you see here, this conventional way of speed control with varying the armature resistance is not required. So, we have already talked about phase control converters using thyristor controller. So, this will give fast voltage control. Then, instead of controlling the R here, see, the more resistance you include, the losses will also be more. So, we do not want to increase the armature resistance other than what is there with the motor design, present design. So, if you see this equation, what way we can control the speed, then the next parameter we can control is only V, that is armature voltage. So, and we have already studied armature voltage, that variable DC voltage, how we can control. Okay. So, let us take when the voltage is controlled, how the speed torque characteristic. This is torque, this is speed. So, armature resistance, R is the armature resistance. So, if you take here, let us say for one speed, see, here also as the torque increases, because of the armature resistance is there, slight droop will be there. But this is the omega 1 due to 1 V1. Now, if you reduce the V2, omega 2 will vary. So, we will get a parallel curve here. Now, again V2 you change to, see, this is for V1, V2, V3. So, by varying the applied voltage V, we can have many parallel curves. We can have a fine speed control. This way it is possible. Fine speed control is possible. Okay. So, by varying we slowly go to this one. Suppose let us take in our drive scheme. I am running at present I am running here. Now, I want to go to this speed. That speed has to be reduced. See, if you see here, and suppose assuming with the load we are staying here somewhere here with the torque, this is the load torque. Okay. Suppose this is the case, what I have to come here. I have to come here means already motor is running at this speed, whatever the depending on the torque curve here. Now, to reduce it, already there is kinetic energy in the system. We have to take back the energy from the system as fast as possible, so that the system can decelerate. Okay. Take back the energy means we have to reduce the current to 0, and then back EMF should drive the current back to the source. So, the power is reversed, such that machine will slowly decelerate. So, our front end converter should be capable of receiving the able to receive the power. If the many front end like a phase control converter, if we use it, it may not be able to take current may not be able to reverse it. Then what we have to do? There we have to somehow dissipate it. So, there are different type of braking. Let us talk about different type of braking. One is regenerative braking. Generative braking. 2. Dynamic braking. Then 3. Plugging. Or it is also called counter current braking. Okay. During regenerative braking, as I told, the stored kinetic energy in the rotating system will be converted to inert electrical energy and pumped back to the source. So, source should be receptive for that one. So, part of the energy, mechanical energy will be converted to electrical energy and pumped back to the source. So, source should be receptive. Our front end AC to DC converter, the PWM converter is capable of doing that one. Power can flow from both sides to the negative with the unity power factor. That means here the alpha should be 180 degree. Okay. That firing angle, the current phase shift between the input current and the input vein should be 180 degree. So, power, that means power will be going from the source side to the other load side to the source. So, many times we will not be able to have a source which is we will be able to which is able to receive the power from the source, like phase control converter. So, but then if you want all 4 quadrant operation and the source is also capable of receiving power, see this all depends on the choice of the front end converter depends on the cost, what is the cost required and the power level. So, suppose if we use the regenerative is not possible, then we will use dynamic braking. What is meant by dynamic braking? In dynamic braking, instead of regenerating back, the energy is dissipated in a resistor by disconnecting the armature from the source supply and connecting to the resistor. See, here it will be, it look like this. See, previously it was like this, field winding we are not touching. Okay. There is a back EMF here, EB, machine is still running because of the inertia of the system is so high, we will not be able to quickly change the speed, but we can change the current direction quickly. That depends on the electrical time constant. Here back EMF depends on the rotation and it depends on the mechanical time constant. So, mechanical time constant will be usually large. So, here we are going to give a resistance here. If you see here, previously we have a voltage source here and the machine was running. Now, we want to reduce the speed or we want to stop the machine. Stop the machine, we cannot immediately we cannot remove the power supply. If you immediately remove the power supply, previously there was a current flowing in this direction. Current cannot change instantaneously. So, we have to slowly reduce the V such that when the V slowly reduce, it becomes less than EB, the current will come to 0. That is the current flowing from the source to the load come to 0. Now, there is a back EMF here. Now, we want the source load to supply current back to the system. So, sensing this 0 current, we can immediately switch on a resistance here, so that current will reverse, and this current depends on the maximum rated current. This resistance will choose such that, see, if the resistance is very small, the current will be very large. So, quickly system can come to a 0 state, but that is not possible. For a machine, there is always a rated current, because the current value depends on the heat generator, on the thermal energy of the thermal management of the system. So, the current, a rated current is always specified. So, we have to limit the current flow in and out of the machine within that range. So, we will choose R such that for the maximum EB with the maximum speed, this current will not go more than the rated current. So, once the R is connected here, system will slowly come to 0. So, if you see the torque speed characteristics, if you see here, now I is equal to EB by R, and we are neglecting the armature resistance because this R will be much higher than the armature resistance. That approximation we can do. Now, T is equal to K phi into I. So, here I, if this current direction we are taking as the positive, this current direction we will take it as negative. So, that to show that the power is negative. So, here it is I is equal to minus I, K phi minus I. So, this will be equal to K phi into minus E by R. Okay. See, this again we can write it K phi into E is equal to also minus K phi. Now, the speed will slowly reduce. So, speed is a function of time, we will put it this way, K phi omega t by R. So, now the torque speed equation when the resistance is connected, this will be equal to minus K square phi square R into omega t. So, in the torque speed system, if you draw the thing, this is our torque, this is our omega. Previously it was, this was our working point. Now, here first you have to make the system to come this level. This level means torque is 0, so current will be 0. Then we have to apply the resistance such that large reverse current, rated current will go through this resistance. So, the reverse torque will come here. From there slowly, that means from this point it will come here. So, from A to B, speed is the same, speed cannot change instantaneously. A to B, if you see this point, A to B, the armature current will come to 0. From this side to this side, and quickly, because R is connected. So, quickly current will go to a negative maximum torque decided by the our R. Okay. Then from there, it will slowly, it will along this direction, it will slowly come to 0 here. This will move this path, it will come here and slowly it will come here to 0. So, why? As the speed increases, speed decreases, current will decrease, torque will reduce and slowly come to 0. When it comes to 0 here, the back EMF will also be 0, speed is also 0. But what we want not to stop, we want to see here also it is dissipative, dynamic braking is dissipative, but many of the medium power applications the power is very less because this resistance is connected not continuously, only for a small duration during acceleration and during decelerating the machine or trying to stop it. So, momentary dissipation is possible. Now, another way of doing it is as the plugging, which is seldom used. See, plugging means the polarity of the motor is suddenly reversed. If the armature voltage is suddenly reversed, heavy current will flow, reverse current will flow and system will come to stop immediately, but that is seldom used. Maybe for low speed, the speed is so low, quickly want to make it 0, we can momentarily we can reverse the voltage, so that with the low back EMF and this applied voltage, still the current is, the quick sudden current is well within the maximum rated current. That is called plugging. So, what we want in the high dynamic performance application, we will be using, this is the best way, regenerator, some of the power is taken back, or but this can cost of the system can increase, or quick braking by dynamic braking, okay, dissipate it. This can be used for speed control also, okay. Not only speed changing the speed, not change the speed to up to 0, okay, speed lowering the speed also it can be done. So with the voltage control, how effectively with the good dynamics what we can, how we can control the speed, that we will study now. Now let us talk about the how dynamically with the, how we can control the torque speed characteristics. See, here we have assumed so far the flux is constant, okay. So with the constant flux, what is the speed what we can go? The rated speed, okay. And is there any way, any other way we can slightly increase the speed above the rated speed? So let us see the torque speed characteristics like this. Here axis I will change it for convenience, this is T, okay. Now we are controlling the voltage, so slowly voltage we are increasing, so motor will start from 0 speed. So as the voltage increase linearly, when it comes to here, the maximum rated voltage means speed has also reached to the maximum rated speed, okay. Now in this region, suppose this is torque, okay, depending on the current, the torque region can be anywhere, okay. So we can have for the same speed, we can have any torque point here depending on the current. So with the voltage, suppose in this voltage here, omega here, let the machine is taking the maximum torque, that means current is maximum. So torque is also maximum here, we will mark the maximum torque here with a different color. So machine has gone to the maximum torque here, T. Now hereafter we cannot increase the voltage, because if it increase the voltage, what will happen? It may be going beyond the rating of the machine, okay. And voltage and current also we cannot increase it, because we have come to the maximum torque now. Suppose if we want again speed control, it is possible. See, we have one more degree of freedom. We can control the flux, we can reduce the flux. So reduce the flux means we know its EB is equal to K phi into omega. Okay. So, and at this point, if you want again increase the speed, means we can reduce the omega phi such that EB is constant, maximum rated value, we can keep it here. So, here from this region, above this region, this is called omega base speed. So, by EB is constant, that means V is also constant, and if it is a current is also constant for the depending on the torque, we will reach the maximum power region, but torque is variable. So, from here onwards, this is called constant power region. See, we have reached the maximum voltage and current. We cannot go beyond this one. So, this power is limited, but the speed we can change by changing the flux. Now, how it will have, how it will be? Let us say T, we know it is K phi into I, armature current, okay, and we know T into omega is equal to P, power, and for a separately excited machine, what is back EMF? K phi omega is equal to V by I armature. Okay. So, from this one, what is phi? From this one, phi is equal to V minus I R by K omega. Okay. R is constant, I is constant depending on the rating, V is also reached the maximum value. So, if you see here, all this gives a constant value. So, phi will be equal to some constant A by omega. Okay. Now, let us take phi is equal to A by omega. So, what is torque? Torque is equal to K into A by omega into I, and K is constant, A is constant, I is also constant. We have reached the maximum level. So, this can be right thus, that means T is equal to some constant K2 by omega. This shows T omega is equal to constant. This is called constant horsepower. So, whenever we are changing the flux with respect to speed, we are in the constant horsepower region. Okay. Now, if you see here, torque will be inversely proportional to phi. When we slowly change the phi in proportion to omega, torque will be inversely proportional to omega. So, here if you say the speed torque characteristic, it will go like this. See, up to how much we can go, this, that also depends on the bearing and the mechanical design. Usually 1.5 times, 2 times the above base speed we can go. Okay. So, we are using the 2 degrees of freedom, one is the armature control, one is the flux control. So, when we do the flux control, we said it is a constant power region. So, here this region is called constant torque region. So, constant torque region means full this speed we can have constant torque irrespective of the speed up to the maximum. But here above base speed torque is not constant, we cannot have the maximum torque available is limited. So, it will go like this. Now, how do you have a speed control system like this, that it can go above base speed and below? Is it only possible after the phase control converters or AC to DC converter? People could realize before it was not possible, but as engineers, you know, one beautiful thing about the engineering is engineers always have a solution for everything, that depending on the situation. Okay. So, in olden times the speed control system, this is possible, how you control it. Okay, dynamics may be slightly not as fast as possible, but we can have a speed control, all 4 quadrant as all regions variables. Region means below base speed and above base speed also, it is possible. So, how it was done? And initially we sought the resistance control. but resistance control is not economical, its efficiency will come down. So, we are not using resistance for speed control, and how it can be done. Let us say one very famous system, it is introduced around 1890s, the Watt-Leonard system. See, we have a motor. This is our motor which you have to run below base speed and above base speed. Okay. So, we require a voltage control. So, what we will give, we will use this our drive motor. I say drive. This we will give it to another separately excited motor which is working as a generator. So, I will put generator here. Okay. We have a DC line here. DC line we will draw with a different color. This is the positive side, negative side. Okay. So, this machine has our field winding. So, field winding we are connected here through a rheostat, we will connect it to the positive side here. Okay. So, this shows by varying this resistance we can have the field voltage also is in our control. So, that also we are going to use it. Now, to this machine the load is connected, load for variable speed. Okay. We have this generator. This generator is mechanically coupled to another motor. Okay. All this shows the mechanical coupling. So, we have another motor. This motor is directly connected to the our DC supply, and the field winding and the field winding for this motor also directly connected. Here, that means the motor, this motor runs at constant speed because it is directly connected to V. V is not in our control. Okay. Now, there is a generator. This generator supplies the variable voltage to drive. So, how do you get a variable voltage here? See, for this one, this generator field, again we can control through a resistance. Okay. Okay, we will connect it here. We will connect it. So, the machine is running our motor generator set, this one, motor and generator. This motor is running at constant speed. Okay. Now, by controlling the excitation of the generator, motor generator, field excitation, variable armature voltage can be given to our drive motor. Okay. So, this machine will work in the constant, now it will be working in the constant torque region, that is this region. Armature voltage is controlled, we can have constant torque depending on the load here. So, slowly we are increasing the armature excitation, that means we are slowly cutting down the resistance. When it comes to the this resistance is 0, that means this field excitation comes to the full field excitation as excitation of the generator as that is a rated excitation. So, machine has come to the drive has come to the full speed omega b, our drive motor. That means armature voltage has come to the full. Now, hereafter above base speed, what we will do? By controlling the field winding of the drive motor. Now, this drive motor field winding will slowly introduce the resistance, so that the excitation voltage will reduce and flux will reduce, and from here the system will go this way, inversely proportional to torque, this. So, we can have variable speed operation here. Okay. This way we will do it. So, speed control is possible here. Okay, but this is not the, for the in the modern drive control. This is somewhere in 1890s, I think it is introduced. This is not the one we are using, because this dynamics is very poor. The mechanically we are doing it, and there is a lot of dissipation is there, because resistance involved, field in the field circuit. Okay, so efficiency of the system will come, but it's a reliable system. It can work. We can have variable speed operation of the machine, and this is, if you want to implement this one, we require a lot of. It's very expensive. For the drive motor, we require another generator and another motor. Okay, so three motors are required for to control one motor. But this way also we can do the thing. But what we want for high dynamic performance application, we want to control through our phase control converters or variable voltage control using PWM converter, so that fast control is possible, and we are not going to introduce any resistance. So, dissipation should be less, so efficiency should be maximum. That means fast dynamics and maximum efficiency. How it can be done? See, let us again go back to the torque speed characteristics. So, how it can be done? How it is done with the voltage control using our controlled converters. But let us take the torque speed characteristics. Again, this is our T, this is our omega. Okay. Now, the system is running like this. Okay. Now, our previous equation omega with respect to T, omega is equal to V by K phi minus T into R by K phi square. Okay. So, this is, we got this one. Now, let us say our system is running at this speed for a torque. This is the low torque. Now, I want to reduce the speed to this one, this point. Sorry, I want to reduce the speed to this point. This is here. So, now we are working at this speed here. No, sorry, at this speed, because of the load, the speed is here. I will go for a different color. Now, this is our present speed. Okay. Now, I want to go from this to this speed. So, system is running. What we have to do? We have to make the current supply to the machine to 0. Using our controlled converters, we will slowly reduce the firing angle such that quickly current will come to 0. Now, current will come to 0, and again what we will do, when the current will come to 0, when the applied voltage is equal to EB, again we slightly reduce the voltage, the current EB will supply current back to the source, assuming the source is capable of taking this one. Now, we will again slowly reduce the voltage, so that we want to draw the maximum current from the machine, such that the maximum negative torque is applied. So, with the maximum negative torque, the system will be able to decelerate very fast. So, if you see the curve, system is running because of the mechanical time constant, the speed cannot change instantaneously. So, speed is still constant. So, when the current is maximum current depending on the TL to 0, we will be going from this speed to, this is the region, we will go from A to B. A to B, I will reduce to 0. Okay. Then as the current increases, now the torque is negative. So, this equation instead of negative, it will become positive. Okay. So, this curve, that means this curves we can extend this region, all these parallel curves we can extend to this side. So, this is during the regeneration period. Okay. Now, but the speed cannot change it. So, system will go to many through various parallel curves and come to the maximum torque, negative torque, depending on the machine rating. That is the TL maximum, where I is equal to maximum negative. Maximum negative. Now, what happens? So, from here to here, the regeneration starts. This is B, it will come to C. Regeneration starts. So, in this region, torque is negative. So, load is supplying power to the machine. Now, what happened? Now, the regeneration starts, machine will slowly decelerate. So, A to B to C, the current changes, it is very fast. Now, C, now the mechanical time constant will come into picture and this will slowly reduce. Okay. Now, this is our rated speed. We want the next speed is somewhere here. So, machine will come to this speed, slowly slow down, regenerating. Okay. Now, we want to, now the back EMF has, now speed has come to our rated speed. Here again we do not want the rated speed to go down. So, we will sense this one, the converter voltage will slowly increase, such that slowly increase means these are the curves. The machine will slowly go from this region. So, the speed is constant. So, that what we are doing, we are going in this direction. That means the regenerative power we are reducing it. So, that way the regenerative torque, negative torque slowly will reduce and quickly the system will come here. That means it will go to various parallel path. Okay. So, B, C, D, E, that is during the path through B, C, C to D, D to E. That means B to C to D to E, it will be regenerating. From here onwards, current will increase in the positive direction, machine will give drive power to the machine and machine will quickly come to this region. So, A to B current decreases, B to C is the electrical time constant. Then from C to D it is a slow process, that is a mechanical time constant, and machine has come to the required speed. Then from D to E, E to F, we are adjusting the current, driving current or the current from the machine such that we are controlling, so that machine will quickly come to the stable state. So, there are electrical time constant, mechanical time constant involved. So, this we have to properly sense it and control, so that machine should come to the proper speed without any overshoot or without any overshoot in current, and current should not go beyond the rated value. At the same time, any regeneration we should take the maximum torque, we should develop the maximum negative torque from the machine, so that machine will accelerate or decelerate with the maximum time constant possible. Now, this is from the torque speed curve. From the time domain, how it should work, how a typical response curve for the torque speed characteristic and the voltage characteristic, and also the EB with respect to time, we will study in the next class.